RMS value is very important in working of AC circuits. We can classify RMS value in two parts, that is RMS value for current and RMS value for voltage. RMS value for current can be denoted by IRMS and RMS value for voltage can be denoted as VRMS. RMS value is also called as effective value or virtual value, but popularly it is known as RMS value. In case of DC, if we draw the graph voltage versus time or current versus time, then it is a straight line indicating the magnitude of either voltage or current remain constant with time. But in case of AC, the magnitude of either voltage or current is not constant with time. It fluctuates from minimum to maximum. Here it is a minimum, here is a maximum, here is a minimum, at A minimum, at B minimum, and at C it is a maximum. And between the A and C, it is slowly increasing and becomes maximum, and after slowly decreases and becomes 0. Then after that turn to the negative cycle here. Again in the negative side, this is the largest value in the negative side. Again slowly it becomes 0. So in DC, the magnitude of current or voltage is constant with time, but in AC it is not constant. It is changing from one value to another value, from minimum to maximum. Here is the current I here, but we take the current. Suppose I take the half cycle here, then here is the magnitude of current I1, here is the magnitude of current I2, here is the magnitude of current I3. This is the largest value, that is denoted by I0 or Imax, the largest value of the current. Similar for voltage also. So largest value of voltage can be denoted as a V0 or Vmax. Then again the value of the, here is a I4, I5, etc. Now let us understand what exactly the meaning of RMS value of the current. Here I got two circuits. One is the DC circuit, another is the AC circuit, and some current is flowing through the DC circuits. When the current is flowing through the DC circuit, it becomes hot. So when the DC current flows through the resistor becomes hot. Even in case of AC circuit, when the AC current is flowing through the resistor, it becomes hot. This idea we can utilize to define and to understand the RMS value of current and voltage. For the DC current, let us denote it by IDC, that is the DC current, that is IDC flowing through the DC circuit, and I and the suffix AC, that is flowing through the AC circuit. When current is flowing through round the circuit, in both AC and DC, work is done. So when the current is flowing around the circuit, coming back, then work is done. Similarly, in case of AC circuit, current is flowing, coming back to the same position, work is done, and heat is produced in the resistor, and this heat is dissipated. So there is a dissipation of heat. We can say dissipation of power. So both in case of AC and DC, there is a dissipation of power while current is flowing around the circuit. For DC, the graph is like this, parallel to time axis, and here is a suppose current. So, but for AC, let us draw the graph for half wave. For DC, the value of the current is remaining constant, I equals to constant. For AC, I is not constant. it changes with time. Like this is the first current I1, another current I2, another current I3, and so on up to the IN. So every time in AC, every time the magnitude of current is changing, but in DC, always current is remaining constant. So in case of DC, work done is converted into heat energy. Heat energy. And what is the formula for energy? Energy nothing but, formula for energy nothing but voltage into current into time. But V equals to IR. Therefore, formula for energy is IR into I into T. Therefore, formula for electrical energy is I square RT. What is E here is the energy. And electrical power equals to work done upon time. That is I square RT upon T. This and this gone here. So we got here the electrical power equals to I square R. Now here is a DC current. Therefore let us say power in DC. Power in DC can be well denoted by, in place of I write down IDCR. So this is the power in case of DC circuit. This is the formula for power in DC circuit, that is I square, and DC is a suffix. So I square, the DC current square into R. Now for AC circuit, here is the current I1. For the current I1, power formula is I1 square into R. And here is a current I2. For current I2, the power formula is I square I2 square into R. Similarly, for the I3, the power equals to I3 square up into R, and so on up to the N current. The power formula is IN square into R. So let the first power is P1, that is I1 square R. Power for the second case P2 equals to I2 square into R. Power for the third case is I3 square into R, and so on. Power for the nth case Pn equals to In square into R. So total power in half cycle of AC equals to P1 plus P2 plus P3 and so on plus Pn. So we need to calculate average power. So average power, that is a P average. P average is nothing but how many divisions? There are N divisions. N divisions. Therefore, average power P average equals to P1 plus P2 plus P3 and so on Pn divided by N. This will provide us P average power. Now P average equals to P1 plus P2 plus P3 and so on up to the Pn divided by N. So what is the P1 value? That is I1 square R plus P2 value I2 square R and P3 value I3 square R and so on up to the nth value, that is In square R divided by number of division, that is N. Now taking R common, so R equals to R into P average equals to R into I1 square plus I2 square plus I3 square and so on In square divided by N. So this is the average power. I would like to ask you one question. Why we are calculating average power? Pause the video, think a bit. Okay, I tell you. You see, in AC circuit, the magnitude of current is not constant. Every time the magnitude of current is changing. So we cannot use the 10-20 different values to calculate the power in AC circuits. It will be very complicated. So to make it simple, what you do, you calculate the average value of the power. So average value of power in AC circuit is given by R into I1 square plus I2 square plus I3 square and so on, IN square divided by N. Now consider two cases. Left side we got a DC circuit and right side we got AC circuit. In both cases, a resistor R is connected across the supply, and in both circuits the resistor value is same. Suppose it is left side 5 ohms, then right side is also 5 ohms. The value of resistance is same in both cases, and in both cases the current is flowing, and current is flowing for the same time. Let us call the time equals to t. So current flowing for the same time. When the current is flowing through the resistor, in both cases for DC as well as the AC, the heat is produced across the resistor. So let us call heat produced in DC circuit H1 and the heat produced in AC circuit equals to H2. Now we are going to consider a case when the amount of heat produced equal, that is H1 equals to H2. I repeat, in both cases the resistance value is same, in both cases time is same, in both cases the heat produced is same. So these three factors are same. Now we have to consider one more factor which is same. When the same amount of heat is produced in both cases, the power dissipation is also same in both cases. Implies when resistance value same, the time value same, and the heat produced is same, implies power dissipation in both cases also same. In both cases also same. So what is the power here? What is the power here? That is a PDC. And what is the power in the AC circuit? That is a P average. So when R is same, time is same, heat produced is same, then their powers also same. That is a power in DC circuit is equals to average power in AC circuit. So power in DC circuit is nothing but I square DC multiplied by R, and average power in AC circuit is given by I1 square R plus I2 square R plus I3 square R plus and so on IN square R divided by number of division, that is N. So I square DC into R. Now taking the R common, so we have I1 square plus I2 square plus I3 square plus and so on IN square divided by N. Now cancelling both sides R value, so we get I square DC equals to I1 square plus I2 square plus I3 square plus and so on IN square divided by N. Now taking square root both sides, taking square root both sides. So we get here IDC equals to under root of I1 square plus I2 square plus I3 square plus and so on In square divided by n. This value of DC current is nothing but called RMS value of current and denoted by IRMS. Therefore, IRMS equals to under root of I1 square plus I2 square plus I3 square and so on In square divided by n. Now let us generalize the above concept. Now consider a periodic function, and for periodic function, how to write the expression for IRMS. So for periodic waveform, above expression can be written in form of integration, that is IRMS equals to under root of here, if it is a periodic function from 0 to t, so total number of divisions are t. There are the small number of divisions, so number of divisions we take t. So in terms of integration, the IRMS value can be given as 1 upon t, and integration starting from 0 to t, and here is the I of t whole square with respect to t. What is I of t? I of t nothing but instantaneous value of current. It is nothing but instantaneous value of current. It is given by some function. So it is some expression given some function of t. Similarly, as we have obtained the RMS value of the current, we can also obtain the RMS value of voltage as well as. How to calculate? For example, VRMS you wish to find out. So VRMS equals to under root of V1 square plus V2 square plus and so on Vn square divided by n. By using this expression, we can even find out the VRMS value. After all this discussion, now let us define the IRMS and the VRMS. Now first of all, define IRMS. It is a value of IDC, that is the DC current. It is a value of DC current which would generate the same amount of heat. I already told you that when the current is flowing through the resistor, heat is produced. So it will produce the same amount of heat in a given resistance for the same time as done in AC circuits maintained across the same resistance. Then IRMS is given by I1 square plus I2 square and so on In square upon n. So this is the basic definition of IRMS. Similarly, we can define now VRMS. It is a value of VDC, that is a VDC nothing but VRMS under special condition. What is that? What is the special condition? Which would generate same amount of heat in a given resistance R as done in AC circuits. That means we have AC and DC circuits. In both circuits, the same amount of heat is produced. If both circuits have same value of resistances and current flowing for the same time, then VRMS equals to V1 square plus V2 square and so on Vn square divided by n. So these are the definition of IRMS and VRMS. Now let us prove that IRMS value is equals to I naught upon root 2. What is I naught? I naught nothing but maximum value of current. It is also called peak value of current. Here for one complete cycle, let us take time t equals to 0 to time equals to capital T. So time span is 0 to t. We have to find out the RMS value of current for time 0 to capital T. Here I have the DC circuit and the AC circuit. In DC circuit, while current is flowing, the heat is produced. The heat produced can be denoted by HDC. And while current is flowing in AC circuit, the heat produced is nothing but HAC. Now condition to find RMS value of current is nothing but heat produced in DC circuit is equals to heat produced in AC circuit, provided the resistance values are same and current flowing for the same duration of time, where HDC is equals to DC current square multiplied by R into capital T, and HAC equals to integration 0 to T, and here is I of t whole square R into dt. Therefore, since what we are having HDC equals to HAC. Therefore, I dc square RT equals to 0 to T I of t nothing but instantaneous value of current R dt. We know that instantaneous value of current is given by I equals to I naught sin omega t. This is the formula for instantaneous value of current in AC supply. So we are having I square dc RT, and here is 0 to T. In place of I of t, this is nothing but I of t. I of t nothing but I naught sin omega t. So here what I am writing here, I naught sin omega t whole square multiplied by R with respect to t. So this is equals to 0 to T. Left side is I dc square RT, and here is I naught square sin square omega t R and integration with respect to t. So what you can do now, you can take common I naught square common, and R is common, integration 0 to T sin square omega t with respect to t. So left side is we are having I dc square RT. Here I naught square R and 0 to T sin square omega t can be written as 1 minus cos 2 omega t upon 2 with respect to t, because of trigonometry formula sin square theta equals to 1 minus cos 2 theta upon 2. This is trigonometry formula. So from that formula, sin square omega t can be written as 1 minus cos 2 omega t upon 2. So this is equals to I naught square R and 1 upon 2 taken outside, integration 0 to T 1 minus cos 2 omega t with respect to t. So left side is I square dt RT. Both side R and R get cancelled. So we have I square dc multiplied by capital T equals to I naught square upon 2 and integration 0 to T 1 minus cos 2 omega t with respect to t. So this is I square dc multiplied by t equals to I naught square upon 2. Now doing integration, integration of 1 is t, and integration of cos 2 omega t nothing but sin 2 omega t divided by 2 omega, and here are the limits 0 to t. Applying limits, so we have I square dc t I naught square upon 2, here is t 0 to t minus here 1 upon 2 omega, and here is sin 2 omega t, and limits are 0 to t. This is equals to I naught square upon 2, upper limit minus lower limit, minus 1 upon 2 omega and sin 2, and omega nothing but 2 pi upon t, and this is t minus 0. Therefore, I square dc into t equals to I naught square upon 2, here is a capital T, minus 1 upon 2 omega, t get cancelled here, sin 4 pi. But the value of sin 4 pi equals to 0. Therefore, I square dc into t equals to I naught square upon 2 multiplied by t minus 0, implies I naught square upon 2 into t. Now both sides capital T get cancelled. We get I dc square equals to I naught square upon 2, taking square root both sides, taking square root both sides. Therefore, I dc equals to under root of I naught square upon 2, I dc equals to I naught upon root 2. But from definition, I dc is nothing but equals to I RMS. Therefore, in this equation, replacing IDC by IRMS. So IRMS equals to I naught upon root 2, because IDC is nothing but IRMS. Hence, IRMS equals to I naught upon root 2 is proved. The relationship is established. Similarly, VRMS equals to V naught upon root 2. In a similar manner, we can establish relationship VRMS equals to V naught upon root 2. Thanks for watching this video. I hope your concept regarding RMS value of current and RMS value of voltage have been cleared. Please give me your suggestions and give me your feedback. How do you find this video? Meet you again with another topic. Till then, wish you good luck, all the best. Before saying goodbye to you, I would like to request you like, share and subscribe the channel. Bye bye, meet you again.